All right, good morning everybody. Today is a bit long lecture. So good morning everybody. Today is a bit long.
So YouTube close for it.
So sorry. I'll try to cover some area of CFD people are using for respiratory flow modeling, and also a little bit of cilia movement, and also the molecular dynamic simulation. That very, very briefly, but mostly the computational fluid dynamics. So, just guess how large is the surface area of an adult lung? Do you have any idea how large it is? And also guess how long is the aggregate length of our airways? Do you have any idea? Because we have very tiny lung here, but the surface area, how much? The surface area is like a tennis court. Okay? If you just combine all the surface area of a lung, it will be like a tennis court. Okay? And the length, if you connect all the airways, the length will be from Melbourne to Perth. So, it is about 4,000 to 5,000 kilometer. Okay? So, it is huge. So, before we start this lung modeling things, I just need to give you some lung anatomy, because this is the term sometimes I use. So, if you do not know where it is, so it will be hard for you to understand. All right, you see the left image. So, there are two ways we normally inhale the air, through nose and through mouth. Okay? And also when we take the medicine, we also use both. Okay? Like the inhaler we use mouth, but there are some other things. There are some other, I know that for COVID, they also spray something through the nose. Okay? So, there are some medicine we can use like both in nose and through mouth. Okay? But we found that nasal drug delivery is more efficient than the through the throat. But it's a very complicated airways through nose, and it has couple of names. You see from the nose, and then we have nasopharynx here. They call it nasopharynx. It's on top of your just tongue here. Okay, and then oropharynx. Oropharynx is here, just your vocal cord, just up there, and then we have hypopharynx, and then we have larynx. So, larynx is a very, very complicated area. It actually connect your upper airways with your trachea. Okay? It is very, very tiny there, very, very small, tiny. That is the reason, even though your Reynolds number is very, very small, even 100, still you can experience the turbulent flow, because very tiny there. So, the local Reynolds number is very high, because the velocity actually accelerate there. And then we have a long trachea. This is the trachea, long trachea, and then it separate this and that. And then we have how many lobes of a lung? Do you know how many lobes of a lung? Anybody? So 5. There are 5 lobes. And do you understand why you have, it is not symmetric, why you have 2 one side and 3 other sides? Yes, because we have heart. So, heart actually occupies some space. That's why we have 2 on the left and 3 on the right. Thank you. So, and from here we just specify how we understand that. We just specify this one we call like a generation 1 or generation 0. Some researchers they call it generation 1. Okay, then it bifurcates into 2. So, this area they call it like a 1. and after that 2. So, this way we have 23 generation. Okay? So, 23 bifurcation or 23 generation. So, that means, so how many outlets then we have? How many outlets? We have one inlet. So, how many outlet? Anybody? 2 to the power 23. Okay? So, we have huge number of outlets. So, that is why when you do the modeling is a very hard. You have to specify all those outlets. So, you need a very big screen and get all the outlets to specify the outlet boundary condition. So, in that way we have until generation 18 we can easily identify, but after 18 we cannot identify. They are actually covered by acinus. Okay? Acinus means the alveoli actually start from there. So, we have here like a balloon like structure. Okay? Here you can see, and then this one is actually the alveoli sacs. So, you know what the alveoli does is just exchange the oxygen and the carbon dioxide. Okay? And Professor Chakraborty already explained about the capillary or blood flow. The capillary means the smallest the channel through the blood actually passes, the very, very smallest. So, near the alveoli, this is actually the smallest capillary. Okay? Smallest capillary is near the alveoli, on top of the alveoli. There is a reason for that. Do you know why? Because that capillary is very tiny, and the red blood cell, the diameter of the red blood cell is about 6 to 8 micrometer, but the radius of the capillary may be 3 to 4 micrometer. So, that means when the red blood cell goes through that, it actually squeeze a lot, squeeze and its membrane expand. So, once its membrane expand, it actually exchange the due to diffusion, exchange the oxygen, okay, and carbon dioxide, take the oxygen and release the carbon dioxide. So, the red blood cell collect all the carbon dioxide from our cells. Our body is always working. So, they collect those wastage things like carbon dioxide and some other wastage material from our body and bring them to the heart, and heart actually pump to the lung, and lung then purify, take the carbon dioxide and give the oxygen, then it come back to the heart again and then pump the red blood. But when it comes to the lung, the color is like a bluish color, because no hemoglobin that time. So, that is why those capillary is very, very tiny. So, we will discuss this one later on, and this is some CT scan based geometry, and I will discuss about how we do it. So, now why do we need to study the lung? Because it is especially for the modeling. So, yesterday Professor Chakraborty told that not always possible to do experiment or some other study, because you cannot take your heart out and lung out and do the experiment. And also through the numerical simulations or computational fluid dynamics simulation, you can analyze a lot compared to the experiment. Experiment you just get very, very limited results. But numerically you can do whatever you like to do. You can probe any points and then you can analyze the results, but in the real life, real experiment is not possible. So, you see here the air quality in Delhi. So, you know what is the air quality now in Delhi? This is the winter season. Okay? So, you see here, and we are inhaling lot of these dust particles. Okay? So, you know the stubble burning, right? You have a stubble burning near Punjab. So, they burn the rice, okay, the paddy things, and then it actually produce lot of unhealthy smoke, and it comes to the Delhi, I guess, and that is the reason it's so polluted. So, if we inhale this one, how it actually affect our lung? So, that is what we need to study. And not only that, we have some other pollution. That pollution is like car exhaust pipe produce lot of ultrafine particles. So, there are a couple of sizes we need to consider. It's called PM 2.5, PM 10 and more than that. So, PM 10 means the particle size less or equal to 10 micrometer. Okay? And PM 2.5, it means the particle size is less or equal to 2.5 micron. Those are very dangerous because it goes very deep airways. Okay? When you inhale the ultrafine particles, it goes very deep airways. But PM10 is also dangerous. Recently we found that it's also dangerous, but more than 10 micron, it normally stuck. At first, it's stuck in our nose here. See, we have a lot of hair inside the nose. It has a purpose. Sometimes we see why we have hair in the nose, but it has a purpose. So that actually stop, okay, all the particles you are inhaling. That's the first barrier. And then the second barrier is our mucus layer. Okay? So our all conducting airways has a mucus, very sticky mucus. So mucus, any particles actually go on the mucus, it's actually deposit. And then through the mucociliary clearance, we are actually eating every day. I mean, every 10 seconds or 15 seconds you are eating, right? You feel some itchy after 10 to 15 minutes and you are eating. So that means all the mucus is coming up. It's a one-way movement. One-way coming and feeling something itchy here, and then you can just eat. So this is the way mucociliary clearance is happening. So a lot of barrier before it actually attack our lung. But if it is like very highly toxic particles, so there are some problem. It can penetrate into the epithelial tissue. And then the other thing is air quality in Dhaka. So Dhaka also the similar as in Delhi. So they have also, they are champion for a couple of years. I found that they are on the second most polluted country, capital city. And there are a lot of things happening. So that's why we really need to understand what actually is doing it. The another recently thing is that I'll show you later on. That's called the micro and nanoplastic particles. Not many people know yet because we are everyday life. We are using plastic bottle. We are using plastic bag. So those things are actually affecting severely to some marine life. Okay? So not only that, we realized recently that it is also in the air. You know why? We are using the water bottle and throwing it outside, and it is exposing the sunlight, and with time it is becoming very hard, and then when you like is interacting with something and becoming small and tiny, like a micron or nano-sized particles, and then it is actually on the air and we are inhaling it. So recently we found that in our body, almost every organ we have it, like in kidney, in respiratory system, in blood, even in mom's breast milk, we got the this tiny microparticle. So now it is also very dangerous, but we don't know yet what is the consequence of having that. Okay, so we found that maybe it makes some lung cancer or something, but still there is not much medical evidence. So that's why still we cannot say that no, don't use plastic things. We cannot say very strongly. So that's why we need to do some research. So what is the source of PM 2.5? In 2015, these are the recorded. Only 59 good days of air quality in 2016. This is based on the Dhaka, okay, in the Dhaka city. Maybe very much similar to your Delhi. Only 59 good days. All other days are like full of polluted. Over 80% of urban residents are exposed to air quality levels that exceed the World Health Organization limit. So they have some air quality limit. I think it is 80 or something. And it is always more than like 200 or more than 200. It's very dangerous. And 20% reduction in exposure to urban air pollution would save 1,200 to 3,500 lives annually and avoid 80 to 200 million cases of illness. Okay. So in 2015 alone, Bangladesh had 122,400 numbers of death attributed to PM 2.5. You see how severe it is. And Dhaka ranked 44th in terms of PM 2.5 pollution and 71 in coarse dust pollution, PM 210 in 2015. So now, normally it's a typical day who are doing servicing or like doing some jobs, how they spend their time. So most of the time they spend like home, about 42.8%, okay, of their whole day, 24 hours, they spend at home. And then outside 8.23%, office 38.23%, and out and about 10.73%. So that is the average one people use. And we breathe between 4.5 to 42.5 liter of air per minute. It depends on you are resting or you are running or you are sleeping. Okay. So that means we breathe in one day the total 22 crore PM 2.5 particles. You see how much it is? 22 crore, right? Yeah, 22 crore PM 2.5 particles we are inhaling in every day. So that means we are breathing about 220 million tiny PM 2.5 particles per day, just over 2,500 per second we are inhaling the ultrafine particles. And where are we breathing these particles? Home is about 23%. We are actually producing a lot of these particles at home, especially in the village, in the countryside. So people are using like wood burning. Wood burning, they are producing a smoke. That smoke is very hazardous. Last time I came in 2022, I came in Kharagpur, and that time my family, my brother's wife, came to Kolkata for the treatment, the lung treatment, and she had actually COPD. Okay, then the doctor said, "You should not have COPD." I said, "Why?" Because he's woman, he's not smoking. So why? I said, "No, she is cooking every day, 3 times a day, in the morning, lunch and dinner, and it actually producing a lot of smoke, and that can affect." So the doctor argued with me, and at the end she actually died in couple of months. Okay, so that's why not only smoking, that is called another kind of smoking, who are cooking in the kitchen in the countryside. So that smoke particles is also very dangerous. So now a little bit about the background. So initially it actually started before 2000, and I was very lucky that the guy who started working Hoffman in 1990 paper is a very famous paper. Luckily I met him in QUT in Australia, and that guy actually started working on it, like the modeling, and his student Farkas. I am also collaborating with this guy. So they started with a very simplified geometry. Okay, it's not like a realistic geometry, just a bifurcated geometry, because it is very hard that time to get the lung image. Okay, and then slowly it actually developed, and sometimes they got like the mid hunter, that is a mouse lung. So they try to many ways to improve, because those results they published there, it is far from the reality. Okay, our realistic lung. So that's why we need a very good realistic lung to describe the real things happening in our lung. So that's why we just collected some CT scan image when we started in 2012. We just started collecting some CT scan images of a lung. Okay, and then we started doing some post processing. You can see at the end. So and but when you do the post processing, you see here the lung actually is covered by the parenchyma thing. So you have to clean it up to get the airways. But when you clean up, some part of the airway is actually damaged. So you have to reconstruct it. So it is not a very simple job. But yeah, so when you do it, you see after the first processing, we get on the left side, and a lot of rubbish is still there, and some airways already gone. So we have to do some manual fixing it. Okay, you see here. So those after the fixing the manual things, we just extend some cut of things here. You see, we extended the airways. Okay, and then these are the geometry we got at the end. Okay, so now still all the airways, the outlet is now closed. You can see the outlet is closed. Also there are some holes on the surface, so we have to fix as well, and that everything we have to do manually. Okay, and then we get the surface segmentation like this. And now you see on the top, that one is closed, the outlet is closed, then we cut up, okay, and apply the outlet boundary condition. So these are the final geometry. So this final geometry we got about 13 generation, because after that is very tiny and is very hard to get, because a couple of micron size diameter, and it is not possible from CT scan. We can do it. We can do some manual adding. We can add some manual way, but that will not be some realistic things. I think the 13th generation is still all right, and we also got the nose and the mouth both. Okay, so but in Australia it is very hard to get the ethical clearance to get this data from the hospital. Yeah, it is possible, but it is a very long way to do. So that's why I contacted someone in India, and we got the lung CT scan from India, and the India one was from here, because when you do the CT scan, they cannot do the whole lung CT scan. So they have to do part by part, from here to there and from here to there too. So I got this one from here in India, and I got this one from China. And then I connect together. Okay, so here you can see it's connected. It's connected here. It's a larynx. You see how tiny here. So so this is the complete geometry. So then we apply the mesh. We did an extensive mesh dependent test, because we had to face a lot of issue with publishing paper, because as I said before, everybody's lungs are different. So we cannot compare my results with your results, because our lungs are different. So how can you compare it? So that's why we have to make sure that our numerical results is correct. So that's why we did a very extensive mesh dependent test. We use 3 different types of mesh. This is called the hexa mesh. Okay, and you know the control volume we already discussing for last 5 days. Okay, so these are the equations we solve, the continuity and the momentum equations, and then we have the turbulence K omega model we use, and then the energy equations. I use the energy equations for some application of our lung as well. So here we applied some realistic breathing pattern we got from the experiment from the hospital. So what is the profile of this breathing? Actually it was like some discrete data, the one that TA showed you last time, and then from there we draw the profile and we just get some mathematical equations, and then we wrote the UDF. But there is some other way that he showed you how to use the discrete data as a boundary condition. Okay, but you can also do this. So you can see I used 3 different boundary condition. One is called the 60 breaths per minute. So that means when you are running, okay, you breathe very fast. And then resting is 30 breaths per minute, and then 15 breaths per minute when you are sleeping. So 3 different breathing pattern we use. The maximum for the resting or sleeping, it takes about 4 minutes per breath when you are sleeping. Sorry, 4 seconds, not minute, 4 seconds. 4 seconds on breath. And you see very interesting that it is not a sine function, but before we saw a lot of papers, they published this breathing pattern as a sine function, but this is what we just got from the experiment, and you can also experiment by yourself. When you inhale very fast and then slow down, and after that you give a bit pause. Okay, when you breathe out, a bit pause and then you breathe in again. So there you see at the end we have some pause. And then so how our conducting airways is made of. So you can see the mucus layer on top, okay, and underneath we have some cilia. Cilia is like a brush like structure. So we are cleaning the floor, right? That's a brush. So we have a brush just underneath the mucus layer. The brush is actually cleaning up. So brush is working like this always. Okay. So pushing up and going down and then pushing up. So this is the way, it is one way movement. Okay. The cilia is going down, but that way. So this is the way it is always happening, and then the cilia actually is floating on the water, and underneath the water we have the epithelial cell. So that you see how many barriers is getting. So but still, if some of your particles are very toxic, you can easily penetrate into the mucus layer, and then through this cilia it can actually go to the epithelial cell. Okay, this is our schematic of how we did our numerical validated results. We use 4 mesh density design, okay, and then we use 3 mesh element design, and then we use 3 mesh boundary prism layer design. Okay, the boundary layer we showed you like a 6 layers, right? We showed 3 mesh boundary layer to see the result is changing or not. And then we use 4 pressure velocity coupling schemes. So we have a lot of schemes like simple leg, Pichot, a lot of things. So we just use 4 of them, and then we compare our results and perform the mesh independent test. And at the end we got the result. So if you really want to see, because this is the very extensive way we did, and we just published this one in a book chapters. It's very details. The paper is the book is not still is not in the market yet. It will be very soon. So now you see the 3 mesh, the top, and then the mesh element we just give on the boundary layer, okay, how we define, okay, and then we did some mesh dependent test, okay. So this is the way we calculated residual, and then we just did some for density 1 to 2, 2 to 3, and 3 to 4, and then we compare our results, okay, from there, and then we just got our validated model. And this is the other way, in just we locally validated our model as well, like the nasal, the oral, the larynx, and from generation 0 to 13, okay, and we just also calculate how many particles actually escape, go out from the lung, from the outlet, okay, and not deposited. So this is the way. So this is for 3.8 million, we still call it coarse mesh, okay, and medium mesh 5.1 million cells, and fine mesh is 7.8 million cells. So this is the way you also compare our results.
What is the y-axis here?
Y-axis is the deposition fraction. Okay. So now these are some comparison with some previously experimental data. Okay. So as I said, it is not very quantitative. Result is quantitative, but you cannot directly tell that why it is not the same result as that, because of this every lungs are different. So that's why I said if it's close to that value, still accepted. So these are different lobes, okay, and these 2 experiment data, and this is my previous PhD student, his result is that, and our current result. So for different tetrahedron mesh, hexa mesh and the polyhedral mesh. So, these 3 type of mesh we got, result is almost similar. Okay. Again, as I told couple of you that there are some other way we do some validation, that is like for a specific part of a lung, it is in the trachea. Okay. You see for the trachea here, we just some other researcher, they calculated the deposition efficiency with the normalized particle inertial parameter, and then they have the results, and then we just also got our results, and then it actually follow the trends. So, in that way we see it is in the range, okay, in the upper limit and the lower limit. So, in that way we also validate our models. So, this is the maximum we can do validation for the lung. Now, at the end we just got this geometry, and these are the results we got. And then when we in 2012 we could not get up to the 13th generation, because we did not have those software available that time. So, that time only we got only this part. Okay. And then we just use about 10 million unstructured tetrahedral cell, and we use the fine boundary inflation layer, hexahedral mesh we put on the surface, and then dense tetrahedral element at the bifurcation region. Okay. And then we did some mesh dependent test, and then we just study the 10 micron size particle deposition for 15 liter per minute flow rate, 30 liter per minute flow rate, and 60 liter per minute flow rate. And as you can see here that when the flow rate is very high, more particles are deposited because of the turbulent effect. Okay. Turbulent means it is going here and there, and then once it is it touches on the surface, it actually deposits. So, if you use any use the Ansys fluent, there is a boundary condition called the trap boundary condition. So, trap means when the particles hit the wall, the particle will be disappeared, and then we record the coordinate on that point for the post processing. Okay. Because this particle is not the real particle in Ansys, it is just point particles. Okay. So, that means we only record the coordinate points, and we take all the coordinates at the end and get the geometry, and we just see this deposition. Okay. It is not like a particle is moving and going this way, this is actually deposited, is already in the a deposit in those area. So, from these results what we found that when the flow rate is very high, that means when you are running and we are breathing this dust particle and these things, it actually deposit on our upper airways a lot. And not only that, there is other hot spot, we call it hot spot, is this area, this bifurcated area. So, in biology they call it carinal angle. So, in that carinal angle here particle actually deposit. And another thing is when it actually clear, the mucociliary clearance time here is very slow. Okay. Because it is coming from this way and coming here, is coming from this way and here, and then slowly moving from here to there. And you observe that if it is there for more than 7 hours, okay, the particle will be deposited inside the epithelial tissue if it is toxic. Okay. And this medium one is also you can see some more, but for slow breathing means laminar flow. When it is laminar flow, it actually follow the streamline of our air flow. Okay. So, if the flow follow the streamline, it actually goes along and it can go to the deeper airways. Now, here we see some quantitative results. All right. So, we just draw a line along the y axis, and then we see you can see from where those particles, most particles are deposited in for 3 different cases. I should show this one together, then you can see. So, that one is actually from here to there. Okay. So we just counted along the y axis and then we showed it here. So in 3 different cases you see the position specific particle deposition. So he see here it is about negative 0.082 or something. So that means it is here somewhere. So most particle actually depositing here. That's why I can see here. Okay. And here we just did for 3 different particle size, 1 micron, 5 micron and the 10 micron size particles. So in that case it was bit hard to do like a polydisperse particle that time in 2012, but now we have the Ansys has very good like system that we can solve the polydispersed particle, and we call those is monodispersed particle. So monodispersed particle means the single size particles. We can only simulate a single size particles. So that's why we have to run 3 simulation, 1 micron, 5 micron and 10 micron. But now you can use like a polydisperse. So I'll show you the in the tutorial how you do that. So you have to give the maximum and the minimum diameter. For example, maybe the minimum is 1 micrometer, maximum 10 micrometer, and then you have to show how you want the distribution. Okay, it is a normal distribution. Then they will show the middle value, the maximum. Okay, maybe 5 micron has the more particles, or you can specify which one has the maximum numbers, maybe 8 or something. Then the curve will be like that. Okay, this way Fluent can automatically distribute the particles. Okay, and here you can see the deposition efficiency in the upper airways. You can see the 10 micron size particles actually deposit for 60 liter per minute, deposit more, okay, compared to the 5 and the 1 micron size particles. So that means we just confirm that the larger particle actually deposit in the upper airways and the smaller particles go to the deeper airways. That's why I said PM 2.5 is more dangerous because it goes deeper airways. So PM 2.5 is like 1 micron. So that means this actually is not depositing upper airways, it is going to the deeper airways. So now this geometry I just got from America from one of our collaborators, and this looks like we call that time is a very realistic geometry, but it is not actually very realistic. What we did is we had some profile, like yesterday Professor Chakraborty showed you that how we get one dimensional path, okay, using some software is called SIM something, right? Yesterday he showed it. Yeah. So yeah, that one. So so we actually had this kind of path, okay, from the medical imaging. We got this kind of path. So based on the path, they actually designed this airways, because already we have the Weibull geometry. We know that the dimension of each like bifurcation or branch, we know the dimension. So if we know the path and if we know the dimension, it's easy to create it. So that's the way we just created this geometry. So until 2015, this geometry was very, very popular. All right. So then we use first and the best available 17th generation anatomical model with entire bifurcation branches. And here we just have 1453 bronchi up to the 17th generation. So that means if it is 17th generation, so the outlet or the bronchi will be about 2 to the power 17, right? But that should be very more than 1453, isn't it? Then why we have less? Because yeah, it is not possible to get all the path. So there may be some of these are only 15, some of these may be 13, okay? But up to 17 we have only 1453 bronchi, okay? The last one. So, and 34 million unstructured dead mesh cells we just got. That is the maximum mesh we use in our HPC. So, our HPC cannot tackle more than that. We can use for PhD student, they can use maximum 64 CPU. They cannot do more than that, but if somebody does some very extensive research, they have more, or they can use the Amazon Web Service. So, they have millions of nodes they can use. Okay. And here we did some pressure and the velocity contours. So, you can see how this pressure is distributed. So, pressure is also very very important here because there is a lot of pressure drop. Okay. When it come here, start from here, see the pressure drop, how much the pressure is dropping. Okay. So, for the drug delivery, so we need to understand this pressure drop, and then we just draw this line along this for 5 different lobes, and then we just calculated the pressure drop. So, these are the pressure drop. You see how this pressure is dropping from about 4.48 or something from there to the 0 is by in some cases for 10 generation is the pressure is 0 already. So, that means there is no pressure after that. And now, here we just use some microparticle deposition during the fast breathing, when you are breathing very fast like 60 liter per minute. So, 1 micron size particle and 10 micron size particle. Okay. So, 10 micron size particle you see it is depositing in the mostly in the bifurcation region and upper airways, and for 1 micron size particles is coming to the deeper airways. So, again we just got from the close to realistic geometry that particle are depositing in the smaller particle is going to the deeper airways. And here we use 1 nanometer particles and 10 nanometer particle size. So, it is a different story because this they follow the Brownian motion. Okay. So, when the particle is very tiny like a nano size particles, they do not follow the particles for like more than 1 micron size particles. Okay. They follow differently because they actually like Brownian motion. Brownian motion means it's like going here and there. Okay. Yeah, it's dispersed here and there. So, that is why it is like work a different way. You can see is work as a different way. So, the 10 micron size particle goes to the deeper airways, but the smaller particle is actually deposited on the upper airways because of the dispersion effect. In Bengali, we normally call it like the rice puff or muri or khoi. Okay. When you just do using the how they call it like sand, this goes here and there, right? It's similar to that. It actually happened there. And then we started. So, this is our first study for polydispersed particles, and we published in that scientific report journal, and it is from 1 micron size particle to the 10 micron size particle, and we can easily just find out here the 10 means the red one. You can see the red particles is almost the upper airways, and 1 micron the small one is actually going to the deeper airways. Okay, you can see clearly from there. And then we calculated the deposition efficiency, okay, based on the particle diameter, and we found that up to 10 micrometer, from 1 micrometer to 10 micrometer, we just calculated from the right, left and the total, and we just got some this equation. So, the equation is very very accurate. It is close to r square is equal to 1. So, that means this result actually suggests that if you use more than 10 micron, so we do not need to do the simulation, we can directly use this equation to just calculate it, the deposition efficiency. Okay. So, now the one I just told you, how this microplastic and the nanoplastic particles accumulate in human airways, posing health risk. Okay. So, this is my very recent study, and we did a lot of review papers, and we try to understand what is happening all over the world with this. We published couple of papers, and after that we did some modeling on this micro and the nano plastic particles. Okay. So, you see in the in Nature in this year they published, and they said that 16,000 plastic chemicals compounds found in the plastic, 16,000 plastic chemical. Okay. So, this chemical, and more than 4,000 plastic chemicals are hazardous. Okay. So, I do not know, because the plastic company, they produce those things and nobody cared that time what is in there. So, and they just found that there are 44,000 plastic chemicals are very hazardous for our health. And nowadays we are so much dependent on this plastic, we cannot stop using it. Okay. We can see when we buy some vegetables from the market, we just found they just put like this way in the market with the plastic cover. And we just found that the plastic wrappers are known to release some chemicals into the food. Okay. So, you now understand how dangerous it is. So, in the microplastic and nanoplastic are pervasive environmental contaminants that have been detected in human and avian respiratory systems very recently, not long time ago, very recently. So, these particles actually originate from both primary sources like the cosmetics and secondary sources like plastic degradation. So, what is cosmetic? How they are getting from a cosmetic? So, that means the women are spreading it, right? It's not only women, but you see there are some like some face wash. You know, some people I think they use face wash. In the face wash there are some small tiny particles. Okay. So, if there are some particles, then if you do the cleaning your face, it clean faster and clean nicely. So, those small particles is actually the plastic particles, and when you are cleaning it, this particle is going through the water and going everywhere. So, and it is going to the maybe ocean or somewhere, and then the fish eating, okay, and it is going into the fish because it is not nobody can digest it, and then you are eating the fish, and so you are eating again. So, it is like a cyclic order, it is just is coming back to you. Okay. So, the health impact, so the nano and micron plastics are associated with various lung disorders, okay, including the COPD, okay, the fibrosis, asthma. Okay. So, this kind of disease, and the inhalation of these particles poses significant health risk due to their interaction with biological tissues, potentially disrupting endogenous surfactant and these cytoskeleton arrangements. You can see the baby is born and plastic particle everywhere. And now we can see the hidden things is everywhere in the air. And actually the more dangerous thing is, like recently in Australia and some other developed countries, they already introduced the fully electric vehicle. India also trying to do it, but they do not have any lot of charging station yet. They started building it. Already Australia they declared by 2030 there will be no like a fuel engine like the car engine. They will be replaced by the fully electric vehicle by that time. Okay. But it is good for environment, it is good, but at the same time the battery size is very big and very heavy. Okay. So, and because of that, so the wheel in the tire is very big. I saw the Tesla car. So, the Tesla car battery like the wheel is very big, okay, because to carry the heavy battery inside. So, that because it is heavy and it is actually making some friction with the surface of the road. So, it is producing lot of like a microplastic and nanoplastic. You see, this is another pollution. Okay. Previously, it was fossil fuel pollution, now it is becoming plastic particle pollution. So, we need to think about it. So, the aim of this study was to utilize the computational fluid and particle dynamics to model the transport and deposition behavior of nano and micron plastic particles across the entire human respiratory tract, from the nasal cavity to the 13 things. Okay. And the methodology we use the CT scan based technique to get the geometry, and then we use some different breathing pattern, the slow, the normal and the fast breathing, and we also study the shape of the particles. So, we did different shape of the particle, because this plastic is very strong and it is not like always spherical particles. Okay. So, we use like spherical, cylindrical and tetrahedral shapes of particles, and we expect from this study to enhance understanding of nano and micron plastic particles related to air pollution impacts on health, and to inform the clinical and public health strategies and guide the regulatory policies. Okay. So, you can see here we just inhale those plastic particles, and this is called a spherical nanoplastic particles. Diameter is 1 to 100 nanometer size particles, and the right one is the same spherical particles with a diameter size of 1 to 100 micrometer. Okay. So, you can see the nano size particles actually going to the deeper airways, and once this is finished, then it will start. And on the left side you can see how those particles are actually deposited. So, lot of particles actually deposited on the nose and that upper airways, because of the complex airways into the nose. Okay. So, particle deposit there, and on the left side we have the deeper area of the particle is depositing until the 13th generation, and here you can see from the trachea. So, most particle actually goes here. So, after we published this paper, we got a lot of media attention, because for the public health this study is very useful. So, all over the world, especially in India as well. So, a lot of newspaper in India they published our study, and also in Europe in so many different languages they actually told that this study, they said, I just read their news, they said that some comments, they said that we are keep telling that this is dangerous for our health, but nobody cares. Now see the study. So, what is happening? So, and we got a lot of the interview through the print and also the radio interview, and they just encourage us to do some further study. So, we are actually still working on this area. But as you know that we have a lot of limitation for CFD study. We cannot do anything else other than where it is depositing. Okay. So, we very quantitatively tell that this amount of particle depositing here. After it deposit, CFD cannot tell anything else. Okay. So, to do that you need to do some other study. If you still want to do the modeling, then the molecular dynamic simulation is important. You can do the molecular dynamic simulation, where you can see how this particle molecule is interacting with our lung surfactant, the lipid, the protein, or other surfactant materials, how they are interacting. So, because of that, one of my students is working in this molecular dynamic simulation for these plastic particles. And I took another PhD student, he is working on the mouse, he is working for the like a real experiment. So, he is using syringe, he is injecting the plastic particle through the nose of the mouse, and he want to observe those where those particles are depositing and where actually it is going. Okay. So, he will measure not only the lung, but also the blood and some other cells in our body to observe where they are going. Now, this is another study. This is very interesting because last year I just got a news that the American President Joe Biden is using CPAP because he does lot of snoring at night time when he sleeps. Okay. So, I don't know whether you snore or not, but some people snore at night, like make lot of noise, especially if someone make this noise, I cannot sleep. I have some issue with that. And lot of things happen, especially if the husband does it. So, lot of actually separation happen, divorce happen because of this. Yeah, there are some record of that. So, to get help from this, so these are the machine can help you. Okay. So, this is called for the sleep apnea. So, it is also for health risk as well, because during the day we are conscious and we can keep our like our lung open, but when you get sleep, so the muscle of our lung become relaxed and actually is closed almost. So, when I breathe, it makes some vibration and this makes noise in this vocal cord. So, that is why if we can use any technique that can open up. So, that is why this CPAP machine actually developed. But this machine has lot of concern that because they use for CPAP, they use like continuous positive airway pressure, CPAP, continuous positive airway pressure. So, that means they continuously pressurize the air into your through the nose or through the mouth. Okay. They use this mask. So, that use only nose. Okay. Because there are some people only breathe through nose when they are sleeping. Somebody use both or somebody use only mouth. It depends on the person. So, and then they give positive pressure. So, when they give positive pressure, you are sleeping. So, your airways become large. So, there is no snoring and you can have a good sleep. So, but sometimes people don't understand that whether they have this sleep apnea or not, but there are some symptoms. So, if you feel like very dizziness during the day and very sleepy during the day, very tired during the day, I think you should see a doctor, sleep apnea specialist. And I can assure you that if you use this on, you will have a very good sleep at night time, and the following day you will be very strong in every respect. So, you should test if anybody has this issue who does lot of snoring at night time. So, so it is nothing but there is a machine that only pump the positive continuous positive airway pressure, that is it. It is very, very simple. But our aim was like, because they are giving some positive pressure, the positive pressure can have some surface, they are damaging the lung surface or not, because the shear stress, they create lot of shear stress on the lung surface. So, we need to understand whether it is happening or not. So, that is why we actually did some testing, and we want to model, we want to change something if it is needed, and we found that the current system is okay. So, that is why the company, the ResMed is the biggest company all over the world, the US based company. So, now they actually they got support from our research. Now, they put our results in their website. You see, this is the proof our system is working perfectly. So, what we have done here is we just apply some positive pressure. So, that positive pressure is like you are irrespective of what you are inhaling or exhaling, is always giving you positive pressure. So, that means when you inhale is good, you are getting support, but when you are exhaling, you are not getting support, because you are getting like some obstruction, because you are also getting pressure. So, but because you are exhaling is automatically you are exhaling. So, who has not much like sleep apnea problem is good for them, but who has severe problem, I think CPAP is not good for them. They have some other things. We also did that study as well. So, you can see here the static pressure on airway wall for like without CPAP, the static pressure on the airway wall is lower, it is obvious. And then when you apply this, so is just higher, because we are applying more pressure. So, the airway will experience more pressure. Okay. The supporting force on airway wall for without CPAP is lower, but with CPAP is higher. And the airway wall shear stress and airflow velocity field we found is no effect. Okay. So, these are some study we did with CPAP and without CPAP. So, the pattern you see is almost the same, except some value. As it is too small, you cannot see this number. So, you can see the number here, the number here is like without CPAP and with CPAP. So, this is higher, this is lower. Okay. So, the dynamic alteration in area weighted static pressure, the y axis, okay, through a single respiratory cycle, just like one cycle, a third or fourth cycle we just use it, and x axis is the time in seconds. So, A and B is the upper airways response. So, from that and that, okay, and A and B, and then C and D the middle two, okay, across lung generations, and E and F is the entire respiratory system. Okay. So, it is too little, you cannot see it. Again, because we already validated our model. We already validated our model with lot of experimental results. We are using the same model, okay, applying some different boundary condition, but we are using the same model. So, that is why we said this model is already validated. So, we do not need to further validate this model, but you can do that. I already talked to them, the ResMed, one Indian researcher is working, and I have very good collaboration with him, and he said that he will give me some patient specific data. So, in future I will do some validation. Now, this is called the BiPAP. So, BiPAP means bilevel positive airway pressure. So, this is more advanced. Okay. So, CPAP and the BiPAP. So, BiPAP is like they give more pressure when you are inhaling and less pressure, but still positive pressure, less pressure when you are exhaling. Okay, that for the like very severe person who has like a COPD or who has a very high asthma or this kind of things, they can use this system. So, that actually help them, and it has actually both. So, for CPAP, the range of the pressure is about 4 to 20 centimeter water. This is the unit. I do not know how to convert it from the Pascal, but that is called the 4 to 20 centimeter H2O. So, that is the pressure, but for BiPAP they can handle like 4 to 30. So, that means if they need more pressure, they can use it, but it is strongly recommended, and you cannot actually do the change by yourself. So, you have to go to the doctor, and doctor can set it up, okay, what pressure you need. You cannot do it by yourself, it is very like dangerous. Okay. If you set up by yourself, it is very dangerous. Every time you need, if it does not work, you need to go to the doctor, and doctor can do some assessment and can set up the pressure for you.
So, basically it is dependent on the respiratory strength or something?
Yes, and your health condition and how much you need, then they will do maybe couple of nights, the whole night they will assess, okay, and then they will find the optimum pressure for you.
What volume we are actually inhaling and what pressure it
Yes, yes, that's the way they will do the assessment. Yeah, and this is actually very expensive as well. So the left one is about 700 to 1500 US dollar, okay, and the BiPAP is about 1500 to 3000 US dollar. It's a bit expensive, the BiPAP. But if you can buy the BiPAP, that can actually works both. And those things are the same. The mask and this the pipe is for the same. If you want to change any of these, you need to just change the machine, and then you can just plug in. Okay. So this for the BiPAP we recently submitted. It's not published yet. We are recently submitted, and this time actually we rotate for the visualization to show you. We just rotate this on that side, because if it is this side you cannot see anything. So that's why we just rotate that way. So we just showed here, and then we put a mask like that. Okay, and then in this is now the inlet. So we are actually giving the positive pressure through this one, and then through the nose is inhaling. Okay. So you can see here the breathing volume flow rate at the time. So that is our the input we just got, and now these are the parameters actually we applied. We applied three pressure. Okay, it's called the IPAP and EPAP. What is IPAP? IPAP is the inhalation positive airway pressure, and EPAP means exhalation positive airway pressure. Okay, so the maximum IPAP by minimum like a maximum EPAP. So this is the way normally in the machine it is written there, that what is the maximum 12 by 8, 16 by 6, 18 by 8. Okay, so 12 means the maximum IPAP, 8 means the maximum EPAP. So this is the configuration. So we just applied, and this is without BiPAP. Without BiPAP we did not apply anything, so 0. Okay, then we applied these three configuration, and we just observe. These are the observation. So without BiPAP, and then use IPAP by EPAP is 12 by 8 centimeter H2O. Okay, and then 16 by 6, and then 18 by 8. Okay, so these three cases we I studied, but as I said, I don't know which one you need, so you have to go to the doctor, they can set it up. Okay, the 18 by 8 for you, or 16 by 9 for you, or something, they will set up in the machine, and then you can. We just study these three. People normally use these three kind of scenarios. Now the heat transfer. Okay, we study some heat transfer into the lung. You know why you study heat transfer? Because when I was very small kid, my dad used to tell me when I go out during the winter to use the muffler. You know muffler we use? The guy is using it. Yeah, we use here to close this one. That time I didn't know why do we need it. Maybe to make us warm. So that's it. But when I did this research, I found it is very important. If you do it, is very, very important. Because you know our body temperature is 37 degrees, right? Is 37 degrees Celsius. And if we inhale like a 0 degree or 4 degrees temperature of air, so it will go through your conducting airways. And if the outside temperature is very cold, okay, like about the same temperature as you are inhaling, only the small part here. So that means there is not much heat transfer happening. So that means you are actually your cold air is going very deep airways. So if the cold air goes very deep airways, then it's very, very bad. You will catch cold. Okay, some bronchitis can happen. So that's the reason we just use this kind of things. We just protect our this one. If we can protect this one, it can give you your body release the temperature, and your because your the muffler material is insulated. So, that means the heat will be here. So, when you are inhaling, the heat transfer happened. So, that means your 4 degrees or 0 degrees temperature air can become 35 to 37 degrees when it comes to the end of the trachea, and you are okay, nothing is happening. So, it is so from that inspiration, I just did some study on large density simulation of heat and mass transfer in a human respiratory system. Okay. So, we published so much 2 papers, and this paper is the very extreme cases. The first one we did some like 5 degrees, 20 degrees and 44 or 45 degrees. Okay. And this study we just made the lower minus 20 degree and minus 5 degrees. Okay. And you can just observe the cold air you are inhaling from here. Okay. Your cold air inhaling, by the end of the trachea is almost is getting the body temperature. Okay, is becoming because we on the surface we applied 37 degrees. Okay, but if it is not insulated, it is not be always like 37. It will be lower at the if you go to the outside during the winter. Okay, so these are something in the nose. Okay, this some cross section is just D and E, and they are like here, the cross section here. And also we just realized that, as I told, the larynx area here we can see a lot of vortices happening. That is why I just applied the large density simulation to observe this turbulent effect. So, turbulent is here, but it take long time for the simulation. So, one simulation it take about 2-3 months, because large simulation it takes a lot of time and it needs a lot of mesh. Okay, and so it is very hard to compensate. So, this way you can see how these vortices happen. The turbulent actually happened for this lower Reynolds number. I have to check. I think we use about 7 million mesh for here, but we have to run it for longer time because it is a time dependent. It is not a steady state. Okay, it is a transient. Alias, I mean alias. Yeah, but you have any node problem, like you have sufficient number of node you can use? How many node you use?
The number of meshes compared to k omega, like
Alias takes more mesh, and I think it's not 7 million, I think more than that, because 7 million is for the k omega. I think this one I done information not here, but in the paper we have. I can't remember here, but yeah, it needs more meshes, especially near the boundary, because they just treat the alias, so they treat the boundary very well. So we need to keep more mesh near the boundary. So now we see the detailed temperature analysis from this study reveals that how inhaling cold air at minus 5 degrees Celsius and minus 20 degrees Celsius affects the human respiratory tract, highlighting the system's efforts to warm the air as it moves from the nasal cavity to the primary bronchi. Okay. So the respiratory system's ability to warm inhaled air is challenged at extremely low temperature with cooler region, okay, especially at minus 20 degrees Celsius, leading to a incomplete warming by the time the air reaches deeper regions like the primary bronchi, and that can actually affect. Okay. So the presence of cooler temperature in the lower respiratory tract can cause thermal discomfort, increase the respiratory resistance, or damage the delicate tissues, particularly with prolonged or repeated exposure to extreme cold. All right. Now the another case I am just showing all the cases, possible areas. So, this paper is finished just now. We did not finalize the paper yet for the publication. So, here we just use some helium oxygen mixture for drug delivery. Okay? So, helium and oxygen mixture. So, we just found that for only oxygen we are inhaling, that can cause some turbulent effect in the larynx area. So, that means when we are inhaling the drug, it actually deposit on the upper airways, but you need to send it to the deeper airways, the medicine, but it is stuck somewhere here. So, that means you need to make it laminar. How can you do that? So, if you use helium, so your turbulent flow for air become the laminar flow. So, that means in that mixture we are using about 80% helium and 20% oxygen. So, it is called Helox. Okay. So, this Helox mixture can actually help. You see how this they make mixture 79% helium and 21% oxygen. So, this is acceptable range, but for long time it is not good, okay, because if you inhale lot of helium is not good for your health, but for drug delivery for small time is okay, is approved, but you cannot inhale helium for long time. So, this is the another way of you see the turbulent on the left side. Left side is the turbulent, and then it becomes laminar because of this the properties of this Helox. So, the property actually change a lot. So, you can see this study on you can see on the left one is the only air and the right one is the Helox, okay, and we use 1 to 10 micrometer, 91 to 100 micrometer. So, it is a huge range, and we actually clustered. Okay. So, clustered 1 to 10 in one cluster, 11 to 20 another cluster. So, this is the way we just presented here, but the range is from 1 micron to 100 micrometer size particles, and these are the cluster, and you can see for only air how it is affecting, and for Helox how it is affecting. You cannot see it properly from here, but if we can go to some pressure and the velocity analysis, you can see there. So, here you can see on the left side is the air. Okay. You can see some the particle are actually depositing here. Here is just larger particle also going to the deeper airways. Okay. But they are actually larger particle actually deposit on here in the back of this there. So, you cannot see it. So, it is depositing here somewhere, but when I use Helox, it is going to the deeper airways, and if more you can see here, you can see the control for the turbulent kinetic energy when inhaling air, and B is A is air, B is Helox. So, you can see here high value, okay, the kinetic energy, but here you see the low value. At the same time, the turbulent kinetic energy for exhalation, this is for inhalation. For exhalation, we have for only air, we have some higher value, we just observe higher value. For Helox at 1 second, for exhalation is for lower value and is very smooth. Okay. You can see in that critical region is very smooth, but here we have higher value. So, this is one way for the drug delivery. It is not very popular, but they can actually use it. What else? There are some other things we did some other study. It's called the targeted drug delivery. So, you know that in every medicine there are some side effect, okay, even the paracetamol. So, if you eat any medicine, it has some side effect. You cannot just use it for maybe you are feeling pain here, it will only work here, it will work all over the body. So, that means in some places you do not need it, but you are taking it. So, it is actually is not very good. So, that is why recently targeted drug delivery is becoming very popular. It can only affect in that place, okay, especially for cancer chemotherapy. So, when they call it like a targeted drug delivery, but it is not actually targeted drug delivery. They give some specific criteria. The cell which grows faster, they will affect that, right? That is the way they give the chemotherapy. But it actually attack your hair, okay, because hair grow faster. So, at first it affect your hair instead of the cancer cell. So, that is why just trying to get some targeted drug delivery. So, we just we did not do much work, but here we just only did for we just created some magnetic field. For example, we have some issue on the left lung here. So, we just created some magnetic field here, then we are inhaling the magnetic particles, drug particles, and they are actually going only here. It will not go to the right airways. So, that means it is actually helping you. It is not going and affecting some other places that you do not need it. Now, I just finished my CFD part. Now, we want to talk about some molecular dynamics simulation. So, I will not talk much about the structure and the methodology, but some physics. So, what we did here is that gold nanoparticles we use for drug delivery, we use for two cases. So, our study actually we can identify both positive and the negative. Positive means we can apply this technique for drug delivery, and negative means we can analyze for like pollutant particles. Okay. So, two ways we can actually analyze our results. Those gold nanoparticles also can be treated that way, like the people who work in the gold mining or like the goldsmith who makes the ornament. Okay. Whole day they work with that and they also inhale some gold nanoparticles. So, we need to see how it actually interact with the lung surfactant. So, what we did here is we just did two things. One is the naked gold nanoparticles, okay, just gold nanoparticles, and another one is gold nanoparticles coated with lipid, okay, coated with the medicine. Okay. These two way we just release the particles and then we just observe how it is interacting with the lung surfactant. Okay. So, before that I just want to tell a very quickly about the composition in the lung surfactant. So, as I told you before, it start from the 18th generation and that is the alveolar sacs, okay. And inside the alveoli, so we do not have any mucus here. You remember there is no mucus in the alveoli. So, what we have a thin layer, okay. We have a thin layer is called the lipid monolayer. So, lipid monolayer is having is here, then we are inhaling the oxygen and oxygen is transporting through this because they are very porous. Okay. So, due to different density issue or pressure issue, so they just exchange, okay, from the capillary, the blood capillary outside this lung. You see all the blood capillary here. Okay. You can see the blue. Blue means they just come here, okay, and they are releasing the carbon dioxide taken by the alveoli, and then they are taking the oxygen back from the alveoli, and then they are becoming red and they go back to the lung, to the heart, and heart is pumping the pure blood to your body. Okay. So, now this surfactant has a very big impact, especially when the baby is born, when the baby grow up in mom's tummy. What happened is the last part of their body grows this one, the lung surfactant. Lung surfactant start to grow after 27 weeks, okay, after 27 weeks. So, that means if any baby is born, premature born is 27 weeks, it is very hard to like make them live. I don't know in India, but in Australia, yes, I found couple of babies, they survived, but they need extensive care, because you have to put the baby somewhere artificially, so their surfactant grow and they can use their lung for the breathing. But up to 27 weeks, they cannot breathe by themselves. Okay, so and then when the baby is born, what happened? Did you see anybody? I don't know, but because I had the privilege in Australia, we can stay in the surgery room. Okay, when they do the surgery. So I saw my daughter when she was born. When the baby comes out, okay, they take the leg like this way, hold like the opposite way. Okay, they shake couple of times. Okay, and then they give some pipe to clear the nose and then the mouth. Okay, they clear it because lot of mucus there. So clear up, and then the baby cry. When the baby cry, that is the perfect moment. That is the enjoyable moment, because the baby can breathe. So that is the only time the cry is better. Okay, the other times we cry means we have sorrow and we are crying, but that cry is very important moment. So that means when the baby is born, their lung surfactant actually lapse. They are actually like this. Okay, because they don't need it. They breathe from the mom. They don't need it. But when they come out to the earth, the world, they have to breathe themselves. So that's how when they just cry, that means their lungs suddenly, this one actually make bigger, so they get the oxygen. And then from that moment, they start breathing. So this surfactant, so just that time it goes up, and after that it never collapses. Why they don't never collapse after that? Because there are some physics involved. It is called the surface tension. The surface tension make a major role here to keep the airway open all the time. Okay, so there are two types of surface tension for exhalation and inhalation, because when they inhale then it becomes big, when exhale it becomes small. So small means exhalation, the minimum one is 0 and maximum is 23. So these two parameters. So we actually for our simulation we use the two extreme cases. But now my PhD student is working on, there are some intermediate one as well. But in this case we use only two cases, 0 surface tension and 23 surface tension. Okay, and now underneath this monolayer, inside the monolayer is made up of like here you can see proteins, the lipid, 92% actually lipid and 8% protein. And the lipid has different types of lipid. Okay, so it has PO/PG, PO. So there are a lot of different types of lipid here. They have like a cholesterol about 8%. Okay, PO/PG they have 9%. So different other composition. But since the DPPC is 41%. Okay, so because it is very hard to do the molecular dynamic simulation, because every like these molecules you need to tackle. Okay, so it computationally is it also very expensive. So one simulation I remember it take about 6 months. Okay, so that's why it is very difficult to consider lot of variables. Okay, so we have to limit the variables. So what we did is we just use DPPC and some PO/PG and also vary some proteins. Okay, 1 or 2 proteins we varied. And you can see there are some diseases. I am not talking about the COVID-19. So COVID-19, I think they also had this kind of thing. So that is the most dangerous things. we know that we see sometimes some old people they just tell that the water stored on the lung, something like that, right. So, that water and this water is different. That water they go to the hospital and they take the water out from there. So, that water is between the lung surface and the parenchyma. So, in between there are some water actually deposit. So, they are actually is attached such a way there is no mechanism, like there is no like anatomical things to attach, but the surface tension. For example, if you take two glasses and you put a little bit of water and attach together, can you take it off like this way? You cannot. You have to take this slide. Otherwise, its surface tension is so strong. So, that is the way our lung is attached with the parenchyma, that way. So, sometimes water actually penetrate here. So, that is why they deposit some water and it makes a lot of problem, breathing problem. So, sometimes they need to go to the hospital to take the water, like 1 liter, 2 liter water they take it out. But this water is different. This water means this actually closing your airway sucks. So, it is very hard to take this water out. You need some medicine to dry this water. Otherwise, there is no oxygen and carbon dioxide exchange if it is full of water or something. Okay, so, it is a very severe problem. And you can see how this oxygen and the carbon dioxide exchange happen. Now, this is the configuration. I am not going in very in depth here. So, in the modeling what we do is we just take a rectangular box. Okay. So, it is vacuum, it is also vacuum. So, in CFD normally we just do one side, but in molecular dynamics they have to do like a periodic things both side. Okay. So, these are your the lipid, okay, lipid head group. So, this is the lipid head and this is the lipid tail and this is your water. So, the water and the lipid they have some like hydrophobic and hydrophilic condition. So, they are actually hydrophilic. So, that means the head actually attached to the water and if it is and the tail is hydrophobic. So, that means it goes out of the water. So, this is the way they interact. Okay. And I just give some information here how to use some Martini coarse graining force field. It's all about Newton's second law of motion. So, it is nothing but that one. Okay. And we observe here for single particles, 4 particles, 8 particles, 16 particles and 36 particles. And you observe how it is interacting with the lung surfactant. So, you see 9 particles, 16 particles and 36 particles. So, this is one view from the top view and this is from the side view. And we found that for highest number of particles, some pore actually form. So, pore form means something will go inside. So, it is dangerous. Okay. So, pore formation means your lung surfactant is damaged. Okay. So, that is why the water can go inside or something. So, this is the way it can happen. So, that is why the concentration of the particle, the amount of particle we are inhaling is very important. If we inhale lot of this kind of particles, that can damage our lung surfactant. Okay. So, now see the single particles, how these nano particles actually interact with the lung surfactant. Okay. So, it is not penetrating into the water. So, it is in there. Okay. It is not going. Now, the 9 particles, they are actually interacting there. And then 16 particles interacting, and then that is the 36. Again, you can see the pore formation happen. Okay. So, the last one is the mucociliary clearance. Okay. So, the mucociliary clearance as I told you before, that we have some cilia underneath the mucus, who is using like working like as the brush, okay, brushing your mucus. So in our study, what we have done is we are still working on this area, but initial work was to make the cilia and make the movement. But how to do that? Because it is three-dimensional effect. It is not like going this way, coming this way. Then it is very easy. It is like going this way and then coming back this way, and going this way, coming back this way. And not only that, it is actually going this and that way as well. So both way. So that's why it's a very, very difficult. Then from Singapore National University, we just collected this data from them. So they have like a 12 profile of the cilia movement. They have 12 profile. Okay. So we get all these mathematical equation for this profile, and we applied these things in our model, and then we run it, and then we just see that the profile is moving. Okay. So this is the real cilia. You can see the top it from the experimental from the experiment. We just got this one. So now it is there is no sound for this. So you just see here how you are inhaling those particles, and those particles on the mucus is on the mucus, and mucus is taken up. So you are actually, when it comes here, you are actually eating it. Okay, it's just moving with the mucus, and underneath the mucus the cilia is here. Okay, just see the single cilia, and it see it is not a two-dimensional. It is actually as a three-dimensional effect. It is going in every direction. Okay. So this is the single cilium. We call them cilium, the single. Okay. This is their movement, and then we just multiply with this. So this is the way it. This is the experimental data. Okay. So this is the way they have the movement. They are taking the mucus from there. But this is not the real velocity. The real is very fast. Okay, it is slow just for that. Now we covered with the water, and on top of that the mucus layer is there. So now it is actually taking your mucus from your conducting airways. Yeah, and the particles on top of that. So that see the particle is not penetrating. So it is safe. If it goes underneath, then problem. So it is now taking away. So it is very, very slow, just for the demonstration, so that you understand how it is moving. Now the is increasing from there to the maximum 10 millimeter per minute. So that is the maximum. That is the way is always clearing up our lung. Okay, very, very fast. We have some experimental data as well. Yeah, this is the real one. This is what actual things happening in our lung. How the mucus is taking the. You see all the particles we are inhaling, they are taking away. So this is the modeling we use for 3 different cases. One is 3D cilia bead motion. 3D means all sides it works. One is 2D cilia bead motion, it's called a planar, and one has some steep planar. It is not bending, it's just going there and there. Okay, maybe if somebody has some disease, they have this. So it is my long-term plan. That's why I am collaborating here in IIT Kharagpur, that whether we can create some this artificial cilia or not. Okay, if we can make this artificial cilia, it will be very, very helpful to treat the asthma patient and also the COPD patient who has some cilia dysfunction. So I don't think that it will be very tough, because we already know the profile and it is actually working. Then we can use some biocompatible synthetic or something, and we can put some like a battery, okay, and then we can just put where you have some problem. Because if you don't have cilia somewhere, that means your mucus is not clearing out. So your mucus is stuck there. Okay, so that means it's slowly gathering your mucus and it block the airways. Okay, but if you can somehow put this one in there, that can actually help you clearing up. Okay, so that is my ultimate goal of doing research in that area. You can see the animation, if you can see from the back. The 3D effect you can see from the side view and the top view. Yeah. That's it. Thank you very much. If you have any question. Do you have any question? Yes.
So, in one graph you showed the approximating functions for that micron size deposition, where almost each graph shows the same trend and the function is always some factor times x cube times x square times x.
Something like that. Yeah.
Yeah,
Maybe
and
coefficient different.
Yeah, and
Yeah.
the trend for all the graphs is almost the same.
Almost the same. Yeah.
So, like, if we have multiple such data points, can we prescribe a general function like how it will vary?
That is possible. That is possible. That's very good idea. Yeah, that is possible. That we can do. Okay, so because we already revised our schedule, so after that I can give you only maybe about 5 minutes, okay, and then we can start our next one, the how to use Ansys to model this particle deposition. Okay, just 5 minutes. So we have to finish in 12:25, right? 12:30, something like that. Manipal University?
Yeah, so Manipal.
Gujarat.
So no, it's
You know her?
हेलो
she's doing very well.
हेलो
Yeah, yeah. Because
हेडफोन में लीजिए वैसा नहीं हेडफोन में लीजिए
I'm in the health science.
so my molecular dynamics simulation for that whole nanoparticle.
So
She is the co-author.
She's the one with sorting the system. stuck there.
Yeah, she is. Because when I was at QUT, she was there.
Hello.
So she was the co-supervisor of my PhD student. So she helped. For
Ma'am
this.
does a lot.
Hello. Hello.
This modeling part.
Hello. Hello. Hello.
Yeah, we have the mixture. And the mixture of these things, and we calculate all the properties of the mixture. And that's pretty, like the air. Air also we have properties, right? So we are actually getting all the properties for the mixture. And we are putting that on. It's very simple. Very, very simple. Very interesting this one. We did not publish the paper yet. And we'll submit this. Yeah, some they are doing. That's how we are doing. We also published on paper in a conference paper. Conference paper, long time ago. And I told my student to work on this. So now my another PhD student. So he's a that's very good for the whole year. Because that also yeah. On the tablet.
सर माइक का ना स्पीकर
স্যার বলছি যে এমনিতে আপনি কি জানেন যে সিমুলেশনটা কীভাবে করতে হয়? তাহলে আমি আমার ল্যাপটপটা আপনাকে দিয়ে দিতে পারি অ্যানসিসের জন্য, যদি আপনি ডেমনস্ট্রেশন করতে চান।
আমি এটা নিজে করি নাই, আমার স্টুডেন্ট করছে, তো আমি নিজে টেস্ট করি নাই, এই জন্য রিস্কটা নিতে চাচ্ছি না আমি। ওরা যদি করে ওদের সামনে সামনে বলে দিতে পারবো তখন আছে, কারণ ভিডিওতে ফুল ডিটেলস দেওয়া আছে,
ঠিক আছে স্যার।
তো ছেলেটা খুবই ডিটেলস করছে, কিন্তু আমি এটা নিজে টেস্ট করি নাই, যে তোমার ল্যাপটপে নাই, এই জন্য এখন রিস্ক নিয়ে করতে গিয়ে আটকে গেলে এটা বেশি অবস্থা তৈরি হবে। ঠিক আছে। All right, so now I just want to play one tutorial. I asked my student to develop this one before I come here, because my Mac does not have the Ansys fluent, so I cannot show it here. That's why I told him. He did it very slow and very nice way. He showed all the possible areas that you can do it. I think you just follow that, and if you want to do practice after that, you can just replay, and then you can. I think at first you don't need to start by yourself. Just listen. It's about 40 to 42 minutes. Okay. See how it is. It's mostly everything the same. Only the problem is to how you want to introduce the particles. Okay. There are some tricks. So that tricks, if you know those tricks, because you already know how to model the airflow. Only extra thing is like how to use the DPM model. Just add those particles, distribute those particles, give the particles properties. So that's it. It's not very, very tough. So I'm just playing the video, and if you have any issue anywhere, just let me know. I can explain. I can pause the video and I can explain to you. Otherwise, just listen to it. And it's my Chinese student, so he tried to slow, English very slow, but English is good. He will understand. But if you don't understand anywhere, just ask me. Okay, I'll explain to you.
File location, and we'll start by opening the workbench and find the fluent component. And because we already have the mesh here, .msh file or other formats.
So here what happened is, we already have the mesh file. So we are not showing here the geometry creation and meshing it. So we'll be using directly the mesh file. Okay. You already have the mesh file, and you know how to do the meshing.
Sir, is there any way to get these sort of geometries from some repository or something?
But here we use a long file, only a file. Yeah. That's why for the demonstration purpose. But this geometry is no. This geometry is, that's why I said this geometry is not available. Okay, because once you have this geometry, is not very tough to do the modeling. So that's why nobody wants to give this one. Okay, and that's why if you want to collaborate with someone, then maybe they can share the geometry with you, because it takes long time to create the geometry. So that's why they don't want to give to anybody else.
This geometry is created that
Which one? Sorry.
your geometry.
Yeah.
It is created in this software.
A couple of softwares. So I can show you some. Just a sec. I can show you. Where is my mouse? Oh, mouse is here. I can show you the OneDrive. So this is the proof of this book chapter I said. So this is the techniques of aerostructure modeling. So here we give very details. Okay. So this is the student who is actually explaining here. So this is my student. He is explaining here, and this is my student. She came here for 1 month in IIT Kharagpur to do some experiment. Okay. So in this study, you can see. So start from the very simple geometry, okay, and then a lot of things. He actually reviewed all this study, all by doing by himself, and then this is the details. Which software is used, okay? Everything is very like image segmentation. So in details, it is written here. What kind of software they use, okay? So Mimics Medical. So this is the one software. They use Mimic Medicals, and then also a lot of other softwares is there. For meshing, they use other software. So GeoMagic, they also use a GeoMagic, okay? GeoMagic Wrap. A couple of 3 or 4 softwares actually you use to do this, and step by step everything is written in this one. So once this book is published, so it will be available. So if you are interested, or if you can send me an email, I can share this chapter to you. Okay. All right. So that's what I said. So the only we start from the meshing. We have the mesh file. We use pointwise. Yeah, I remember. We use pointwise software for meshing. So pointwise software is very easy. Easy means you have control how you are applying the mesh. It's not like the Ansys meshing. So in that way, we just use the pointwise, and we generated the mesh, and now import. We will import in here. Okay. No, this geometry is very simple, like a pipe. Otherwise, we can't show it here like a simulation. Yeah.
I'm asking like once the geometry is created, you have used 3 or 4 maybe softwares to create a geometry, but mesh is done here.
Yeah, we just created geometry, all those softwares, and then use the pointwise to create the mesh, and then import in the Ansys.
So meshing is done.
You can do the meshing outside. Yeah, not a problem. Okay, meshing you can do outside.
For meshing also you have used Ansys software or?
No, it is not mandatory. So you can do meshing outside and bring it here. And not only that, actually you don't need this like this system. You can directly go to the Fluent. Okay, there are all the components. Okay.
Is that meshing is created this software using this software?
No, not here. In Pointwise. Pointwise is another software. So we use this Pointwise software for mesh generation, and then we save the mesh as .msh, and then just we read it here. Okay.
That is compatible. We can go directly to setup instead of mesh or geometry. However, if you wish to create the mesh from scratch, we'll have to start from geometry. But in this case, since we already got it, we'll start from setup and double click it, and you have this panel. We can do the double precision so that we can reduce the numerical error. We can here customize how many computer cores or parallel computation that we utilize during the simulation. And here we can set up, for example, 16. Start. And now we are in the panel. Let me see. First go to File and import mesh. So go to the file location. And as you can see, here the software didn't notice our file's existence because I guess our mesh file is from the older version. Now they're using .mesh, .h file. However, our file is not is only .mesh, not without the h file compression format. So we'll just click on all mesh files, and then you can see this file. Or in other cases, you can choose all files. Same. So select it and click OK. And now the computer is loading and doing parallel sectioning of the mesh. Here at the console panel, you can see all the information. We'll just wait for the computer to... I think it's already done. Okay, now here if the mesh doesn't show, you can click on display to show the thing that you wish to present, or that is easy for you to conduct simulation. There are a variety of ways to display your mesh. Here, for example, perhaps we can choose edges and features and display. And here is a simple outline of our tube geometry, or it could be a section of the airway. The dimension is set up according to roughly secondary bronchi dimensions. Okay. And we can close this panel. And now we can start set up the simulation. Here it can be a steady. If you go to the general panel, here you can see that it could be a steady or transient simulation. Here we can enable the transient simulation. If we want to employ a dynamic changing breathing profile, we have to go with the transient simulation. Here we can enable the gravitation. Check the model. Here you can see a coordinate lined up. So now we can see that the y-axis it goes like this, vertical into the tube geometry. We can set up this axis as the gravitational axis. However, you can set up in different direction using the 3 components. Okay. So notice the unit is meters per second squared. Okay. Next, one thing we should also look at is the scale to check that this dimension of your mesh is reasonable. Sometimes when you import meshes from different softwares, the dimension might be wrong. Maybe x max is 2 meter and negative is 2 meter. It'll be a 4 meter in x dimension, and that'll be totally inaccurate. And here you can use scale to change the dimensions. You can scale it down or larger. And now let's go to the models. Here you have a variety of computational model you can enable. For example, here, if we consider energy, we'll have to double click it and click on the energy equation to enable it. But here we don't need it. We'll just go to the viscosity model and choose SST K omega. There's two equation model, and this is a very robust model that can handle reverse gradient pressure gradient for that typically exists in lung geometry simulation. And these profiles are all by default, and be sure to choose SST. It's one of the most advanced K omega model compared to the previous ones. And click on OK. So now you have the viscosity model set up. And next, we could choose the discrete phase. Open the panel.
What is say again?
Will there be turbulence in this case?
Double the speed?
Turbulence.
Yeah, they use turbulence, sorry. Yeah, they use turbulence. Because, I don't know, this student, is he should not use the turbulent, but because he is using turbulent for the whole lung geometry, he used the same model here.
No, so in the whole lung there is turbulence.
There is turbulent, that's I said. Even though for small airways, like as I said, the small Reynolds number, 100 Reynolds number, you can experience some turbulent here near the larynx. Okay, that's the reason they just use the turbulent model. So you can see most of my papers published is all turbulent model.
So there is one thing, low turbulence correction given in there. So should we use that? Because major of the flow is laminar. Only at a certain point it is getting turbulent.
Yeah, that's true.
Should we use that?
Yeah, that you use. Yeah, that's your that different way we can do it. But I don't know how to do it in the Ansys this one. So that's why I use. Yeah. So but in industry, so that's why you can see that the default one is K omega model. Industry they use K omega model in every case, even the lamina. They don't care about that because that is faster. Because they use model. Use model means they are not solving the whole equations. They are actually modeling it, making it simplified. But for research, we should not use it. So because he is very used to use it for the whole lung, so that's why he used this one. But you can use lamina for your case. Okay.
And here you can have a lot, you also have a lot of information here, such as unsteady particle tracking or interaction with continuous phase. I won't go into detail there, but here I recommend to just type in
These are tricks.
like 3 more zeros here, make it larger. And physical models. Now, if we want to simulate like a particle inhalation, like for if we enable supplement lift force, we consider the rotation effect of the particles. If the pressure gradient is also a thing, and there's many things we can choose, such as stochastic collision to model the random collision between particles. But here we'll just go with the Huffman-Lee first for today. UDF are user-defined function that you can employ to model the DPM phase in whatever way you like. And these are all by default. You don't have to change anything. So just click on OK. And now we can add injections. Here, you can create injections. You can create multiple injections actually from here. Sorry about my computer is lagging. So we can name it as injection 0. And the reference frame is here. And the injection type is single or group. Single is it sounds like it releases the particle from a single point. Here from surface, however, it releases particles from a certain surface at the grid point or mesh point. However, it releases group.
Yeah, so I want to just emphasize here. So you see, this is a very crucial area. How you want to distribute the particles in the inlet. So that is very important. Okay? Because when we started in 2012, there was not much way. So now they increase a lot of way to distribute particles. So that time we had only the single. As a source, you can release the particle from the source. It is not realistic. Okay? So now they have a lot of things you can release as a group, okay? Or you can use a surface. Surface is the very important one. Surface means you can distribute whole surface in your nose or your mouth. Okay? Inlet, you can just give that way distribution. Or you can use as a volume, or you can use as a cone, okay? Big to small, so particle is coming through that one. So yeah, now lot of things you can use. Mostly we can use the surface. And not only the surface is, generally they use the note points. So note point means maybe on the inlet surface you have 200 nodes. So that means they can only release 200 particles. But if you want to do more, you can actually do that. So there are some other technique. So here actually he will explain all these things. So we use the surface one. Surface one is the most popular. But you can actually go through each one of them and you can test.
So what is taken in case of volume? Because the next one is cone. Cone should also be a volume. How do you separate for different volumes?
Yeah, I think you should go through each of these. So we did not go very in depth some other cases because we just use for the surface, and we found in that area many people they use only the surface. So I think it is not for the lung, but for some other application they use this one. Okay, there are some particles maybe generated somewhere in some system, so they maybe use that one. So for the lung purpose, the surface distribution is the important.
Single is it sounds like it releases the particle from a single point. Here from surface, however, it releases particles from a certain surface at the grid point or mesh point on the surface. For example, if we choose in surface, maybe we'll have a look at the difference between different geometry names. So we'll have in and in 0.07 let's see what they are faces. So as you can see, the yin is a tiny surface created during the boundary layer creation. It's a thing that typically exists if you use ANSA, ANSA meshing software. However, if you use other meshing software, they will merge the surface, the in and in 007. You can see 007 is the internal surface. If you enable 2, you can see that the two surfaces combined together forms the entire inlet. And now we can decide the injection location. We'll use we'll choose the surface release, and in 007, here we will release particle from this green surface and not from this boundary layer surface. However, in your simulation, you can choose based on your condition. And here are the particle type, and just go with inert material. We can simulate, for example, a water liquid aerosols. So the material is water liquid. Diameter distribution, for example, you want to release particles not of one diameter, say that 1 micrometer, you want to release 1 to 10 micrometer. However, how do you release 1 to 10 a range of micrometers particles? You have to tell the computer that you release it like 1, 2, 3, 4 micrometers, or 1.5 to 2.5 micrometer. Here is the distribution equations that tells the computer how to distribute a range of diameters of particles. Uniform one is the simplest. It's just 1 diameters. We can choose a Rosen Ramler. Let's go with that one. So here are the point properties menus. You can choose variables velocity, the velocity of particles that enter the release from the surface. So in this time, we'll just go with 0 velocity. So the particle are released on this surface at 0 velocity, and I assume the inflow of air will carry forward. And this might not be realistic and might not be what is really happening in our lung, but here is only just a tutorial for you to get use of Ansys Fluent. So start time is the time that I wish to release the particles. Because we're doing a transient simulation, we have start time and stop times. If it's a steady state simulation, this option will not exist. So for transient simulation, we want it that we kind of want the flow field to converge, the continuum phase to converge. We might want it to run a few steps, maybe, run a few steps. After convergence, then we release the particle. It's better for calculation stability. However, when you input these numbers, you should always consider the need of your simulation. The stop time can be 0.5, so we'll release a particle from 0.1 to 0.5 seconds. What else? For the surface injection type, we can also with let's see, perhaps group. Actually, let's just go with surface. Okay. So the total flow rate by default is 1 to the times 10 to the power of -20. Here is also a thing that you need to consider during your simulation. So because we're releasing very few amount of particles, aerosols, we'll just use the minimum one, like barely, almost ignore the existence of these particles in the continuum phase. So here are the minimum and maximum diameters. The minimum is 1 times 10 to the power of -6 meters. That's 1 micrometer. And here is the maximum diameter is 1 to the power of 10 times 10 to the power of -3. That's 1 micrometer. If we do it this way, and this is this 1 to the power of -6 to the power of -4, and this to the power of -5. If we do this way, then we are releasing particles from range from this to this range, and that's if we use the mean diameter as 1 about.
So here a couple of things you need to consider. So one is your start time. Okay. So what he mentioned is, because if you introduce particles and also the air together, so there should maybe some problem with the convergence. So it's better you just run for a couple of time steps, get your solution converged, and then you can introduce the particles. Okay. So that's why he start with the 0.1 second. So in 0.1 second you release the particles. And this is the total flow rate, because we use very small number of particles for this simulation. That's why we use very small rate of flow. The flow rate is very small. And then how long you want to release the particles. Okay. So you can calculate. If it's like a breathing pattern, okay, like inhalation and exhalation, you can also set up. Okay. How long you want to set. You can do everything here. Like you can write some UDF as well. So that's why he just make that those particles will be released from 0.1 second to 0.5 seconds. This is the time you are releasing the particles. After that, only you are inhaling air, nothing else. So now about the particle distribution. So what will be your the diameter, the minimum diameter and the maximum diameter. Okay. So minimum diameter, he use 1 micron size particles. Okay. And the maximum is 10 to the power -4, means 100, right? Yeah, 100 micron. So 1 to 100 micron particles, this one. And now because we are using the Rosen-Rambler distribution, so you can see everywhere is help. So click the help, and then it will open up all the details of these things. So what is this diameter distribution means? and how it works. So everything is very, very details. I think you should sometime go to see it, what it is. So now here he is giving like the mean of these two. That means a mean distribution. Okay, you need this, or you can give like you need more particles close to 100 micron. So you can give like a 80 or 70. So then the distribution will be like that. Okay, this is the way we just distributed.
How do we know that air, because in the material it is only given water liquid.
Yeah.
So how do we know that air is also there?
Oh, here model already there. This is already we set it up. Okay, and this is you see the model at the left side, a viscous SST. No, on the left side, multi-phase energy and viscous SST. So that actually for the airflow, and here is just discrete phase. That is the particle flows. So they are actually combining these two equations.
Five times 10 to the negative 5, and it's like this is 1, this is 100, and this is 50 as the mean diameter. 1 micrometer, and this 100 micrometer is 50 micrometers, and here, yeah, in this way we'll releasing 100 particles, like from 1, 2, 3 to 100 micrometers, not 1, 1.5, 2, 2.5. It's just 1, 2, 3. Yeah, I think so. The spread parameter is the parameters that you use to control the distribution pattern of the Rosen lambda. I won't go into detail about that. Let's see, number of diameters will do is 100, so that is 1, 2, 3, all the way to 100 micrometers. And click on OK. And there you have it, an injection 0. And you can always set up, change the parameters here with this setting. And now to the material, it's already set up because you chose water liquid during the discrete phase here in the inner particle already showed up, and the air material, in case it doesn't show in your place, you can click on anything. For example, the water liquid you just set up, and go to the fluent database and find fluid, solid, or inner particle. You can find fluid, and just go down. You have water, liquid as fluid, but we wish to have air here, and you can just copy. And because we already have it, it'll create a new one, air new, so we just cancel it. Okay. Now you have air and particle material. So the material panel is set up. And now to the seldom condition, the fluids. So here initialize the volume of our tube. We can change or check what is set up here. So it's air, so it's okay. If it is not, you just choose air. And it's the same here because because we're using a different machine software, and this software, when we create the boundary layer, it also creates like 2 surfaces and 2 volumes. One volume for that connect to this surface is the boundary layer volume, and here is just internal volume. So here you can see 2. You can also check here. It's air, so we apply, close. And now so now all the volumes are fluid and are initialized as air, and that's great. If you have other cell zones, you can also set up in the same way. Now to the boundary condition. So here it classified everything as war, and that's incorrect. So we'll just change it in as the velocity inlet. Let's see. Yep. And go to wall again, out as pressure outlines. Yeah, pressure outlines. And now the wall is only wall. We can check and the wall setup here. So if you have DPM, we can, in the momentum panel, you don't have to set up anything. But for the DPM, you have to trap. So that once the particle attach the wall, it will be tracked by the wall, and the simulation stop calculating that particle's trajectory because it's already trapped, and it'll disappear from the simulation. And later on, we can collect data that all the trapped particles' position and time. Okay. So we finished set up the wall, and now let's set up the velocity inlet. Here we can do multi-edit so that we edit the two together, boundary together. So the velocity magnitude we can set up as, I don't know, let's try with 1 meters per second. That's a relatively high number. I assume when we breathe in our nostril inlet, the velocity can reach 5 meters per second. So we'll just go with 1. It's a reasonable number. However, during your simulation, it has to be carefully considered. And just apply. And let's set up the out. We can also display it. Doesn't show. Yep, here, display everything. You can see that this is in, there arrow pointing inwards, and out, red arrow pointing outwards. Click on the middle of your mouth, and you can rotate this object. So let's set up the pressure outlet. It could be pressure outlet or user-defined or velocity outlet, depending on your simulation require. Here we set up a 0 gauge pressure outlet. It's not realistic, but it's just for the time being, we'll just use 0. And the particles, I forgot to set up the particle of the inlet. So our particle should be escape, because when the particle reaches the outlet, it should escape. Apply. So here you can also see here, and the two boundary condition change to discrete phase boundary type change to escape. Here, let's set up the inlet DPM. It should be. So here we inject the particle from the inlet. So we shouldn't choose track because we just injected it. Oh, we don't want it to be tracked. It should not be reflect. Re-inject is one option. That if the particle we just injected it, if it escaped, it went from different and to a different direction. It escaped the computational domain. We just re-injected it again. So using the injection, or simply you can just choose escape. Just let it escape, because in our simulation setup, it's a simple case. It'll definitely not escape. You can just choose this as a default, as a safe one. And the internal surface boundary condition, you don't have to set up anything. It's just, yeah, there's nothing to set up. So now I think we finished the boundary condition setup. What else? Now go to the solution. We can choose the method. Here is a simple method. It's the most simple one, and you use it. It might not achieve the best calculation precision. It might not be stable for complex geometry and complex modeling, but it's the fastest. Everything is default. You can, however, you can change it to to other options. So this menu, if you the first one is it usually is less computational resource required. The final one is most computational resource intensive method. If you all go with the final one, it'll take a long time for you to finish the simulation. However, it might achieve a better numerical precision depending on your topic and your case. The control on the relaxation factors, I will not go into detail about these. So just go with default. Report definition, here you can set up different parameters. For example, you can create new ones. Here, surface report, you can extract data such as area weighted average of wall pressure, or or static pressure, and you can name it as this one by default, and click on OK, and then you have it. You have one more extra report definition of area weighted average pressure, static pressure of our wall, and later on you can plot graph or just export the data of the area weighted average static pressure of our wall. Monitors are residual monitors. You can just choose it. This is how we control the residual. If you make it very small, make it very small, the simulation the software will calculate the residual to these values to consider it step converged, iteration converged actually. So we will not go with that far. However, if you're using a double position solver as we set up earlier, we can go with a smaller value. Okay, just click on OK. Everything is default by default. And report file, we just define a new definition, and here we can see a report file. Here you can plot like delta time and time step, or not importantly, just choose these two, the area weighted average static pressure of the wall and the flow time, and these two numbers will be printed out in a file as an .out file with the location that you choose. For example, we'll just go with default one. and get data every time step or flow time. For example, I want data every 0.1 flow time. You can choose it differently or every time step. So if you have 10,000 time step, you have 10,000 pair of data here. Every time size calculations of every weighted average of static pressure for lung will be printed there in this out file. So click on OK, or you just delete it. If you don't want the file here, you can delete it. And report plot is just the definition that we just created here. The plot you have, yeah, I already selected. Yeah, so that after simulation, it can plot the line graph or a dot graph of this parameter. Let's see. Now let's start the initialization. We'll do with the hybrid initialization. It's usually better. It helps you to stabilize the simulation initially. So just do the initialization here at the console page. You can see that it's already initialized and the value is very small. That's a good sign. Calculation activities, you can enable the autosave to save the files every time steps. So if you like, for example, if your computer run off battery and the computer shut down, but you saved every time step. Here I don't want to enable it this time. However, for your daily exercise or experiments, it's highly recommended to enable the autosave. You can customize the saved data. Actually, you can output these data. There's 107 data you can select to save. Here we already select 36 of them, but you can add more. Click on OK, for example. But here we don't want to enable it, so just cancel it. And now we can run the simulation. After initialization, actually, here we already enabled the results graph. For example, particle tracks. We can track our injected particles based on and colored by resident time or particle ID. Just choose whatever. Point or sphere. And save and display. Because we haven't released any particle during our initialization, so this should be blank. And now go to the reports and discrete phase and go to sample. And here is one of the most important part. We collect the particle that deposited on the wall. So we just click on wall and injection 0, and we can append file and start. So once we click on start and then start the calculation, this file, the machine will create new files and store all the particle information on the wall to this file. Maybe we'll just go with out. We also want to see the particle escaped that pass through these two this outlet surface. So start. So now you'll see warning from console. It says unable to append file because you don't have an existing file to append, so it's creating new file. And you'll see a lot of repeated warning. This is because you use parallel computing. We set up 16 at the beginning, so you'll see 16 repeated warnings. The particle data also parallelized into 16 to calculate it by 16 different cores. So we don't click on stop until we finish the simulation. And now run the calculation. Here is the number of time steps you want to employ or use adaptive. Here you can set up the total time that you want to simulate. For example, 10 seconds. And set up here, you can set up the minimum time step as 1 to the power of negative, let's say 3 should be enough. You have to do some research about that. And yeah, if you set up this way, we can increase the maximum iteration per time step to allow that the simulation converges on every step. However, if your simulation takes 200 steps to converge every iteration, it means that your simulation is not that good. It's not converging. It's very unstable. Ideally, your simulation converges 20 time step every iteration. But here it's just for the sake. Yeah. So now initial time step size. Let's check file. So here is initial time step size. We'll start the simulation with this time step, and we can set up the minimum and maximum time steps and factor. Here is an adaptive time stepping. We can, if the time step is too low, it's too small, we can increase the time step so that we can finish the simulation faster. And the standard to increase or decrease the time step is given here. Then is given where? Is given here. The current number we set up as 1. Yeah. So you can set up differently. Here we use 0.01, and also the minimum time step is 0.01. So if according to my experience, the entire simulation will use the same time steps as 0.01, 0.001 seconds. Okay, let's calculate. Yeah, the computer is taking a very long time to calculate. Let's wait for a few seconds to see if it starts. So here is still saving the file to your location.
He's not very professional. He's not very professional. So I think this is the first time he made video for me. So that's the reason. I think he should stop the video recording now, and he should wait until the simulation is finished, and then he could show the analysis. But anyway, it was taking time. That's why he stopped. He did not do the simulation and did not show it. But still, it's very good. It shows details, and it will be saved in your video, so you can rewind and then you can set it up. But still, we have some time in our hand. How much we have? About we have about 40 minutes in our hand. So if you want to practice, because you already have the file, the pipe, okay, either the bifurcation one or the single pipe. Yesterday or day before yesterday, you use. I think you should now do a little bit of practice and add the particle information, because you have other information already have done for the airflow, okay, and then just add those particle information, and you can run and you can do some testing, okay. So you should do some practice before Professor Chakraborty comes and we organize the final session, okay.
পিরিয়ড শেষ হয়ে গেছে তাদেরকে 100% রিলিজ করেছে, যাদের 5-10 দিন বাকি আছে 90% রিলিজ করেছে। লোকে পরে বলবে না যে তোমার পুরো কন্ট্রাক্ট পিরিয়ড শেষ হয়নি, তুমি কি করে টাকা দিচ্ছ। আমি এটাই বলছি, একটা ধরো টোকেন অ্যামাউন্ট একটা বাকি রেখেছি, কারণ হচ্ছে যে কন্ট্রাক্ট পিরিয়ডের আগে কাউকে টাকা দেওয়া, সেটা তুমি আনঅফিসিয়ালি দিতে পারো, অফিসিয়ালি দেওয়া যায়।
লাস্ট ইনস্টলমেন্ট,
হ্যাঁ লাস্ট ইনস্টলমেন্ট একটা 5,000 টাকা বা কিছু একটা 10,000 টাকা যেটা বাকি আছে। স্যার, হ্যাঁ স্যার, স্যার ভালো আছি স্যার। না স্যার, কালকে আছে, কাল না পরশু স্যার, মানে কাল তো রোববার, কালকে যাচ্ছি না, পরশু দিন। হুম স্যার, আপনার তো উইশ না স্যার, আপনার হচ্ছে আশীর্বাদ। দেখা যাক স্যার, এখন মানে আপনার আশীর্বাদ স্যার, খুব খারাপ স্যার, মানে এবং সেটা মানে শুধুই একটা ব্যক্তির অসভ্যতার জন্য, এর থেকে তার বেশি কিছু করার নেই স্যার। হ্যাঁ পারে তো, অনেক জায়গাতেই, মানে আমাদেরই দুর্ভাগ্য যে আমরা অনেক জায়গাতে খুবই ভালো পাঠিয়েছি স্যার। দেখা যাক স্যার, আমরা মানে সবাই অপটিমিস্টিক স্যার। দেখা যাক স্যার, হ্যাঁ ঠিক আছে, ওকে, থ্যাংক ইউ স্যার, থ্যাংক ইউ স্যার, থ্যাংক ইউ ওকে।
Very good afternoon to all of you, and it is a defining moment that we have come to the end of this Gyan course, which is, I would imagine, one of the very unique courses that have come out of this entire Gyan program, in a sense that it connects in a true sense across disciplines, where we talk about the fluid dynamics, its mathematical aspects, computational aspects, even solid mechanics to a large extent, and human physiology and its clinical implications, and of course a bit of touch on how AI and ML could be used to address these problems. I believe that this particular course, which was disseminated with the support of the Ministry of Education, Government of India, and local support from IIT Kharagpur, which is the host institution, and with scientific and technical contributions from our overseas resource person, Professor Suvash Saha from the University of Technology, Sydney, and of course with the teaching assistants from our group, and overall our ecosystem and infrastructural support. Everyone who participated in this program enjoyed every part of it. Having said that, this kind of course is not something which is very standardized, because this course needs a few, what I would imagine, essential prerequisites which nobody in the world would have altogether, because there are rare persons who have studied physiology and also deep maths and maybe AI, CFD, all these things. One person who has studied on depth everything is not possible. So in that way, the way in which this course can be designed so that it can help people to get into real work which can contribute is a challenge from the viewpoint of designing and delivering a course. We tried our best to address this with a balance. As a teacher, I have always recognized that only giving information is of no value unless we connect it with fundamentals on one side and futuristic purpose on the other. So if these two are not there and simply just disseminating something which is written in the book or in papers or somewhere, it doesn't make much of a sense. With all these, and with due acknowledgement that those who have taught this course, we are quote unquote teachers, but we are also learners, because this is not an area which is so well developed that even the fundamental questions are also well answered. There are lots of open issues which we are also finding it very challenging to understand and answer. So in this perspective, I believe that the entire objective of the course was to inspire you to learn on this subject, and not really to give you all the contents that you will require to do everything, because that is not possible. In that spirit, we tried to provide contents and discussions and explanations and hands-on sessions to make you sort of aware of the different tools and techniques and concepts which connect this subject, and try to take it forward on your own. And that is the spirit of any learning, and learning is something which ideally doesn't train you on the subject but trains you how to learn. That is the most important thing that we all keep in mind, because we have done so many courses in our own student life, and I find that whatever courses that I have done, many of those courses are not relevant anymore. As the era has changed, many are relevant because they are very fundamental and they will remain relevant always, but many are not relevant. But they have at least taught us how to learn new subjects. At least that was the objective. So I think this is a course where we, of course, never attempted to cover all possible material under the earth which is under this topic, but try to give you that essential foundation which will give you the contents, the ideas, and the inspiration to learn more and work more on this topic. In this closure session, I would like to invite a few of you to get your very open impression about what you felt about this course, and perhaps how you would like to take your learnings forward in the future, not in the distant future but in near future. And overall, those of you who are from outside IIT Kharagpur, your overall impression in staying at the campus for these several days, that is also something that you can share. So with this, I would invite some of you. I mean, it is just voluntary, and you can come and speak out. As usual, in such cases, people would imagine that, nobody wants actually to come and speak out. And that is where modern technology becomes useful. So if you are given a Google form and all, you will write something, at least put some bullet points. But if you are asked to speak out, that is where, maybe that is not there. But even then, it is my request to please, just randomly you can come, and anyone. Yeah, please.
Hello everyone.
You can introduce yourself.
Hello everyone. My name is Maharnab Goswami. I am from IISA Bhopal. I am doing BSMS there. I am a third year physics major. So my interest in fluid dynamics basically started from second year, where there was some poster making competition, and one of my friends introduced me to turbulence. So from there I started learning the subject, and since in our university there are no specific courses on fluid dynamics, so all that I have learned till now are from Suman sir's courses and his videos. So I had gone through his CFD course earlier, which helped a lot here also. Like here he gave like the concept of traction vector, derivation of the Navier-Stokes equation, and all that he had done earlier in those courses. So those helped a lot. And for me, this simulation using Ansys was first time. So and also I learned a lot about like how to model cardiovascular flows, or like about physiological flows in general. So that is like for me that is a new learning. So now like I wish to study more extensively on like modeling of such flows, or like using and this was the first time I used Ansys. So like I would also wish to learn about more of its intricacies, how to model various different cases, different types of meshings. So and also about the recent session which he gave on integration of data science and AI and fluid dynamics. So I feel that that is a very upcoming topic. Like in today's time, a lot of the people are interested in these topics. So for carrying on from here, I would like to learn more about these topics and to understand and to contribute in some way possible towards this topic. Thank you.
Hello, hello everyone. So my name is Piyush Olivkar, and I am in my second year PhD from IIT Madras. This initiative is literally very good initiative. This is the new way of learning, where the same field people can come together here and contribute their knowledge. So one example is my room partner. So he doesn't know anything, literally nothing. But when he contacted me, when he asked me everything, then I started giving him some advices. So these are the way you should think. This is the way you can contribute some more. So he got some new aspects. So means even I already knew most of the things. That was fine. I also got some new perspective. I met some people here. So that is actually very good initiative apart from the conferences where you go, you already just see whatever everyone did. But GAN is the program where you actually start from the basics and learn. So thank you so much for this opportunity, and this is really very good initiative. I am happy if there will be more such initiatives.
Hello. Good afternoon, everyone. I am Adarsh Singari from Veer Surendra Sai University of Technology, Burla, Odisha. Um, Before I attend Gyan program in NIT Raurkela, after I convinced to our Professor Pandapatra sir, who did PhD from here on Suman Chakravarti sir, highly respected Suman Chakravarti sir. He inspired me do some courses under sir and go there. You will learn more. And my BTech final year project is on electric vehicle cooling using nanofluids, or simply it is about battery thermal cooling. And I am when in my fourth semester there was a course introduction to fluid mechanics. At that time I did not know about NPTEL, what others. So I just learned Sengel. Then after then there is a book called Introduction to Fluid Mechanics and Machinery, written by Suman Chakravarti sir, Gautam Biswas and S.K. Som sir. I feel once I have opportunity to visit IIT Kharagpur, definitely I meet with Suman Chakravarti sir, because he inspired me, and his books like little lucid language, such a lucid language every beginner can do. In fact, in our college said exergy is a little difficult topics, but exergy is from S.K. Som sir and Suman Chakravarti, little it is easier. And one more event I will share. In GATE 2024 conducted by ISC Bangalore, there in heat transfer actually in our university they said it is very difficult course and hard to understand. And when I written in GATE, all 2-mark question are correct. And I before that I saw convection and conduction by highly respected Suman Chakravarti sir. He inspired me a lot. If I clear the GATE, I am much interested in thermal and fluid science. So if I join in IIT Kharagpur, then definitely I do master project or PhD project under sir. Thank you, sir. Thank you, sir, inspiring me. And this Gyan course is such a like program. Huge topics are there, and this is most relevant and futuristic aspect, which is not taught in universities. And one such program, if I clear GATE or JEE Advanced, then we can go into IITs. But we are active now. Then by these extraordinary courses like Gyan and other courses, internship, we can go and we can test the IITs also. And my experience in IIT Kharagpur is what I think more than that. So it is very pleasure, and thank you, sir, such a platform to conduct and contribute.
Good morning, everyone. My name is Nikas Bharti. I am from IIT ISM Dhanbad, pursuing my PhD in first year. So my overall experience about this course is very nice. I am also a very big fan of Suman Chakravarti sir. When I was in my BTech, then I have done my NPTEL course in fluid mechanics from sir. So that time it was my like a dream to meet Suman Chakravarti sir that time. But now about the course was very nice. It was designed in such a way that it was a mixture of both theory and practical. So the basics means the theory part which Suman Chakravarti sir covered, that was also demonstrated by tutorial classes by Suvash Saha sir. And about the accommodation, I want to say it was quite comfortable. Every facilities was being taken care of. So thank you very much once again. Thank you.
Good afternoon, sir. Good afternoon, sir. Good afternoon, everyone. So my name is Somen Chakraborty. I am a research scholar at IIT ISM Dhanbad. Actually, my motivation to attend this course is that I am doing my PhD thesis on cardiovascular flow. So, moreover, as I have during my masters and graduation, I have done many NPTEL courses of Suman sir. So I know that while doing this course, I will definitely gain some fundamental knowledge rather than getting some practical implications, which I already got from sir's many lectures. And apart from that, getting an opportunity to model a patient specific cardiac artery, and also today Suvash sir's demonstration on nasal cavity was very good for us. Thus we can in our further studies we can implicate all those topics and can contribute something as per our limitations to the society and to our community. Thank you, everyone. Thank you, sir.
Next, who will come? You want to come? No. Come. Anyone from IIT Kharagpur? Any participant? Because you know we have heard from participants from outside. So IIT Kharagpur's participants will anyway know what we are, what we teach throughout. So their perception is different, because they are bored with my classes. Outside people are getting something new, but IIT Kharagpur people maybe they are sort of overfed with these kind of things. So any participant from IIT Kharagpur?
Good afternoon, everyone. I'm Akshay Chetpalli. I work under Professor S.K. Das. I'm from the same CFD lab. So I actually work in fluid and heat transfer applications. But this is a very great opportunity to learn this FSI and about physiological flows. So this is physiological flows is completely new to me. So when I see the works of the Suman sir, so I got very inspired by this about biological things, like how mechanical engineer can enter into a biological completely. I completely inspired by Suman sir's journey. So we are from mechanical background. We generally see the things in a perspective of from mechanical perspective. So how can we enter into biological things? So this is very great opportunity, and I'm looking forward to going in this. I feel very blessed to attend this type of workshop and many more. Thank you.
Anybody more? Okay, so I think we got really very interesting and insightful impressions from a few. I wished we could have got more impressions, but because of limited time in this session, we will move forward. And just with what note was left with the previous this impression, that as mechanical engineers we talk about machines. Now there cannot be any machine more complicated than human body. So in a way that should also be a part of mechanical engineering, what I would say, but the machine is controlled in such a way that none of us understand. So I of course would like to proceed further towards the certificate distribution, and we are very happy that everybody participated very enthusiastically and participated in the assignments and lab exercises, and we would be happy to deliver the this participation and successful completion certificates. And these certificates are very precious because these certificates are under the banner of the Ministry of Education, Government of India, so they carry a lot of weightage in terms of their gravity and implication. But before that, I would like to invite Professor Suvash Saha, who has been one of the key instructors of this particular program, to give his views of few sentences on his impression as he went through teaching in this course and overall stay, and then we will move forward to the certificate presentation part of the ceremony.
Good afternoon, and thank you, Professor Suman Chakraborty. Yeah, it was a very good opportunity for me to come here and teach outside of Australia, because I did my PhD and started my teaching in Australia. Although we have a lot of Indian students there, we are teaching, but here we come and I just saw, I participated a little bit, but I just watched Professor Suman Chakraborty's the huge mathematical derivation, this kind of teaching. It is almost impossible in Australia, because if we teach this kind of very fundamental maths in the class, student will sleep, definitely. So that I have a lot of bitter experience. So I got some bad comments from the students as well. They said, why you are teaching this so mathematics? So we normally ignore this, but it's a very good opportunity for you, and I found that I actually checked. The students very careful, and they are checking all the calculation. The professor was explaining here, and some of you already asked some questions. How did you got this term from there? So I love it. I love your, like, the hard working you are doing here, and you are participating, and almost everybody is coming for last 6 days. You all just came here. It's very good. I'm very impressed just coming here. And this course, yeah, as Professor said, that it's actually a bit general, and we try to cover. So, and here you also have different background, like your interest may be different, but we just gave you a broad area. Now you can pick up which area you want to do some further study in future. And it also open up some, if you are interested to working with myself or with Professor Suman Chakraborty, so you are open, you can come, you can discuss with us. So I'm happy to collaborate with any of you. Or if you are not doing PhD here, if you want to apply in Australia, just contact me. I can give you some guideline. Yeah, that's it, and thank you, Professor, for inviting me.
So thank you, Professor Saha, and I think we will start with the certificate presentation. So we will call the names one by one, and then you may please come and then collect your certificate. So I'm requesting Professor Saha also to stand beside me as we hand over the certificates to the participants. So this is in no particular order. It is not the first rank or anything. So Akshay, IIT Kharagpur. Please clap. Anindita Bhattacharya. Abhimanyu, IIT Madras. Aditya Singh, MNNIT Allahabad. Vikas Bharti, IIT ISM. Roshan, MNNIT Allahabad. Manjunath, IIT Madras. Makrawat Singh, IIT Kharagpur. Kunal Kumar, IIT Kharagpur. Itishree Panda, IIT Kharagpur. Daniel Anthony, Manipal College of Pharmaceutical Sciences. Nabonita Vishwas, Raiganj State University, West Bengal. Mrinmoy Bhaumik, IIT Kharagpur. Mondira Mitro, University of Calcutta. Moharnav Goswami, IISER Bhopal. Pratik, IIT Kharagpur. Sai Teja Bura, IIT Madras. Pulak Kumar Ray, IIT Kharagpur. Prabha Lakshmi, IIT Madras. Piyush, IIT Madras. Vivek Jaiswal, Pandit Deen Dayal Energy University. Vandana Beats Pilani. Saurabh Datta, IIT Kharagpur. Soham Vishwas, IIT Kharagpur. Samir Kumar Verma, NIT Rourkela. Raghav Mundra, Airbus Bengaluru. Priyam Chakraborty, IIT Kharagpur. Pompi Das, Assam Royal Global University. Pavan Dubey, IIT Kharagpur. Anyone else who has not received? Quite a few. Okay, I think Saha. There. Yeah. Hridoy Kundu, Heritage Institute of Technology. Chiranjeev Poddar, Calcutta University. Vishwajit Bharat, IIT Kharagpur. Adarsh Singari, Veer Surendra Sai, University of Technology, Burla, Orissa. Anas Ijaz, IIT Kharagpur. Varun Hegre, NIT Suratkal. Surojit Kundu, IIT ISM Dhanbad. Somen Chakraborty, IIT ISM Dhanbad. Is there anyone still not received the certificate? I think everyone has received, whoever is there in this room. So, with this we come to the closure of this Gyan course. It is my pleasure to thank actually many because of whom this course could have been conducted. Of course, first the Ministry of Education, under the flagship of the ministry this particular program is organized, and they are not only the sponsors but they are also the mentors of this particular program. It is disseminated, every such course, flagship course of the ministry is disseminated through a nodal center. For this, the nodal center is IIT Hyderabad, and they have generously supported us to disseminate the program. Special credit goes to the local Gyan coordinator, Professor Hoimanti Banerjee and her office, and our entire educational technology studio and audio video support. Because of their huge expertise in the multimedia, it was quite easy to not only run the program with the recording but also disseminate it through YouTube, and these are all free to air programs which can be seen at any point of time in the YouTube. And we are of course going to compile all the notes and share with you, but we are also trying to have the final videos in a way that every slide will be clearly visible in the videos. So you can use the videos like as a combination of the verbal teaching as also the content which was there in the slide. I must thank IIT Kharagpur overall for the infrastructure everything starting from on-campus accommodation. So the chairman HMC kindly providing the accommodation for all, and including the guest house accommodation for our invited guest, resource person. I would particularly thank the Department of Mechanical Engineering, because Department of Mechanical Engineering, the head of the department as well as other faculty members, they have extended all the support to organize this event, starting from the classroom or the seminar room, the labs and the lab facilities. If these were not accessible, such a course where you have a blend of theory and practice, that could not have been done. The support staff of the department were very kind, and in fact today being an institute holiday, they also extended all the support so that we could conduct. And finally, the support staff and students from my group, I would like to thank two particular students, Monideep and Utsav, who have been instrumental in working very hard for this course, for both the contents, delivery and everything, and my project staff Biloy, who had taken all the pain to organize the entire logistics, starting from accommodation to transport or some other help, because of which we could have this particular program ending without any glitch. Of course, I might have forgotten to mention certain names, but that doesn't mean that they are important. I have not kept any note in my hand to talk about these, but these names came to my mind spontaneously. And I think that as the local coordinator of this particular course, I myself enjoyed, because this course gave me the chance of learning a few things for my own teaching. And usually when we do research, we get deep into certain things, but when we come to teaching, we have to be a bit broader and more general. And that is what it has given me also an opportunity to learn, because I always keep on recalling Professor Feynman's famous statement that the best way of learning is teaching. So if you want to learn something, you teach to those who are interested to learn, and that is how you will learn. So in that way, although I am not in the other end for learning in this course, but I have also learned. In that way, I would say that we are all very happy that all of you could gather. At least you could have some stimulating exchange of thoughts. I hope all of you have enjoyed the campus life. Now in this particular season, the campus weather and all the ambience is beautiful. And I hope that those of you who have come from outside IIT Kharagpur, maybe for the first time or whatever, this would be just the beginning, and we would be having you at some point of time a very important human resource, be as a senior student, be as a researcher, be as a faculty, or in whatever role, and would be very happy to have all of you. With all these, I bring this program to a closure, and we will all get downstairs and gather in front of the department to take a group photograph, which will sort of symbolize the participation in this event. Thank you all very much.